This is a dropped item. It's pretty simple, even though it wasn't simple going through all the trials to figure this out. There's a lot of stuff going on because there's two different movements. We have rotation and we have a linear movement. The main idea of the box is to get it geared down so that the item does a full rotation after 8 seconds. In order to get the timing just right, I'm using a geared down DC motor. Even with a geared down motor, I need to supply around 0.6 volts. So the easiest way is to use a 555 timer to do a pulse width modulation. So opening it up, what we have is the rotation mechanism. There's another gear reduction, but even this is not enough. The whole mechanism does just pop out of the shell. And so now we're able to see the underside of all the electronics. And again, it's all pretty straightforward. We have the pulse width modulation circuit on the top, the motor, and the battery pack. Inside the PWM circuit, there is a potentiometer that can slow down the motor or speed it up, allowing a range of voltages being provided by the battery pack. Removing the main bar and item, I used a guitar string for the item bar that's being melted straight into plastic. The guides on the bar are from the filament roll that I just clipped off. In order to get this project running smoothly, the key point is to smooth all the 3D printing. And so a lot of sanding was needed to be done on most of these parts. The key parts being the gears themselves, just because of the way it prints on the bed. Building off the build plate can cause issues where the first layer swells out. It creates a burr for each tooth, and so you have to go around each tooth and sand it off. Now dropping the bar, we can see how it moves linearly. As it rotates, it climbs up the rails and drops down. The magnets help smooth out the movements in order to get everything moving a little bit cleaner. The plate has a hole in the center poked out. Sometimes the rod gets stuck within the plastic. The design is flawed because there's nothing holding this ring in place, so it is able to lift out. There are different types of gears that you could use in order to mitigate this problem. Originally, I thought that I could gear down again and it would be enough to slow it. But even with the gear down, we still have to spin it with 0.6 volts. That means this design is better off having the center gear in the middle. This is the original setup I was thinking about doing with a regular hobby DC motor. I removed the top gear because there's a clearance issue with the motor. So now you're going to hear and see why I didn't choose this method. It does end up working, but there's a lot of slop within the gears that makes it really loud. Now switching to the gear down motor. On the same voltage and pressing down, there's a lot less power usage. You can see the motor is not having to work as hard in order to get these gears to turn. Now the idea of gear reduction is that we have to spin this first gear a lot of rotations in order to get one rotation out on the top. And you can see I'm spinning it as much as I can. I have to spin it hundreds of times in order to just get that top gear to move. As a consequence, we do have a lot more torque coming out of this top gear than on the bottom initial. I originally calculated how many gears I would need in order to reduce the original DC motor RPM, but all this is simplified by using the PWM circuit. The circuit is really simple. It has 4 components: the potentiometer, 555 timer, the capacitor, and a Schottky diode. The most technical part of this build was sinusoidal path in order to get the item moving up and down. Luckily, I was able to find a video on how to do exactly this. What makes it difficult is that you have to revolve the path around in a circle. In order to model this, you're able to use parameters, and the parameters allow you to create whichever path you need in a circular motion. So that's pretty much it. Let me know if you have any questions, and thank you for watching.